Hello everyone, my name is Deepak Ganesan and I'm a professor of computer science at UMass-Amherst. And today I'll be talking about some of our recent work on rethinking wearable devices, and rather than using traditional wearables, thinking about everyday clothing as the substrate for sensing various aspects of human health. So when we think about wearable devices, we tend to think about the Fitbits and the Apple Watches and all of these devices we find in the market. All of them are electronics based, so you can have these earbuds with sensors in them, eyeglasses with sensors, rings that can measure sleep, ECG monitoring patches, and of course athletic garments with sensors embedded in them. But a few years back, I got into a discussion with one of my colleagues in chemistry, Trisha Andrew, and she works in this area of functionalizing textiles and functionalizing fabric to act as sensors. So taking cotton threads and silk threads and so on and functionalizing them so that they can actually sense various things. You can also do things like energy harvesting with the same threads. And so this got us, this got us really excited, and we started imagining a new way of thinking about wearable sensing. So rather than thinking about discrete wearable sensors like the ones we have today, we wanted to rethink everyday clothing. So what I show here is sleepwear. We wanted to reimagine sleepwear. How can we turn pajamas into a substrate for sensing things about sleep? And sleep is a very important area in the area of health sensing, because there's a lot of implications. Sleep disorders are a big problem. It's hard to monitor sleep in an unobtrusive and easy manner. It's really hard to monitor, for example, the brain signals. And there's a lot of useful information and research being done in the context of sleep. So we wanted to monitor various aspects of sleep. And the key difference here being that rather than thinking about traditional electronics, we wanted the thread itself to be the sensor. The whole substrate of these pajamas is essentially a thread-based sensor or fabric-based sensing substrate, without discrete electronics in the garment. The only discrete electronics would be the buttons, where there would be a processor and a radio and so on. But the rest of it would just be the standard silk and cotton garments. So the challenge though is, how do we sense using loose-fitting clothing? I mean, the rule of thumb in wearables is that you need a reasonably tight fit in order to get a good signal, and that is the reason why in all of the cases you see on the left, people have embedded sensors, these discrete sensors, in sort of relatively snug-fitting devices, right? The ring is snug-fitting, the watch is reasonably snug-fitting, the earbud is tight-fitting, and so on. But we want to do this with loose-fitting garments, and that is quite a challenge. And the biggest challenge perhaps with loose-fitting garments is that you're not guaranteed that there will be a very strong contact with any particular part of the body. So the idea here was that even though the garment itself is loose-fitting, there's many opportunities where we have enough pressure, and we can rethink how we sense in many different ways. The first way we can think about sensing with loose-fitting garments is that even though these textiles are loose-fitting, we do have pressure between the textile and various surfaces against which we press, right? So if you're sitting on a chair, then your back is pressed against a chair and there's enough of contact. If you're lying down, then there's pressure between the body and the bed, as well as if the blanket is pressing down on you, then also there's a pressure created by that. So there's pressure in various ways. Now, even when you're not pressed against a particular substrate, parts of the body are pressed against each other. For example, if my hand is resting against my torso, the hand is putting pressure on the torso, and that creates enough of a contact that you can, and not necessarily direct contact, but enough pressure so that you can actually extract some of these signals from the body. Now, what happens if neither of these are true? What happens if you're not pressed against a surface and really you don't have much pressure between different limbs? Even then, interestingly, you can rethink how the fabric actually behaves. Loose-fitting fabrics, crumple and move a lot, right? For example, as you're breathing, fabrics move with your breathing. As you breathe in and out, your fabric moves with you. Similarly, as you extend or flex your arm, and as you extend your flex your knee, your fabric is your textile is compressing and expanding. It's sort of crumpling with these movements. And so you have to reimagine what these crumpling and these kind of changes in the structure of the textile can be leveraged as a way of sensing. And so that's the other thing that we can leverage, that the textile itself is a flexible substrate, and the foldings are potentially things that we can sense. So this raises a whole lot of challenges that we address in our research, and I've listed them here. So the loose fitting, for example, is a double-edged sword. On one hand, you have all of these dynamics, the folding and the crumpling and so on, which you can measure. On the other hand, you have a lot of motion artifacts, which can affect the signal. Similarly, large surface area is a double-edged sword as well. Large, compared to other traditional wearables, which is in like one place in the body, like for example, the wrist. The textile covers a large fraction of the body, and so you have a huge sensing area to work with, but also a lot of noise because everything is moving together. There's a lot of variability as well because people are different, their body weights are different, the pressure they apply is different, and so we have to be able to deal with all of these huge dynamic range in pressure and the types of movements and the types of things people do. The opportunistic sensing also means that no one location in the body on the textile is guaranteed to give you a great signal. So you really have to sort of sense everywhere and collectively look at the data from lots of different places on the textile as opposed to one location on the textile. And finally, we're talking about very weak signals, right? I mean, extracting a small signal from the body is non-trivial. And one of the things we quickly realized is that existing textile-based sensors would not work. In many cases, would not work in the types of scenarios and the types of signals that we were looking at. So a lot of this work was essentially a very ground-up effort. We had to redesign the sensor. So from the ground up, there were new functionalization techniques, new sensing techniques, and new ways of analyzing the data and dealing with noise, and then all the way up to the application. So let me show you a couple of quick examples of some of the things we've designed. So the pajama, we call it the pyjamas, sort of physiological sensing pajamas. And so this can measure heartbeats and respiration and joint movement. So again, it's a distributed sensing substrate in the sense that there's lots of different sensor patches and different types of sensors because the types of dynamics in different parts of the body are different. So in the figure here, there's 4 pressure-based sensors, both in the back and the front, to take advantage of instances where there's pressure between the torso and some external surface. There's also a triboelectric sensor which can deal with which can work under very dynamic conditions. So I mentioned as the textile moves with the individual as they breathe in and out, and these tribo sensors can measure those kinds of dynamic signals. And then on the various limbs, on the various joints, we have an additional triboelectric sensor that can measure the folding and the crumpling and the expansion as you fold and expand. You fold and your joints. So let's take a look at cardiovascular rhythm and see how you can measure that. Cardiorespiratory rhythm. So the idea here is that when there's pressure, we can measure the ballistics of the heart. So whenever the heart pumps, there's a ballistic action, and there is it's a very small, very tiny amount of ballistic pressure exerted, but that's potentially enough. So we developed a very sensitive resistive pressure sensor, textile-based resistive sensor that can actually measure these tiny changes caused by these ballistics. But you can get a lot of very interesting signals from the pressure. So the baseline gives you things like posture, which side you tossing and turning when you're sleeping. The envelope gives you the respiration signal. As you breathe in and out, the envelope changes for this pressure signal. And then finally, these tiny ripples are caused by the ballistic signals of the heart, and you can measure the heart-related signals from the ballistics. And then, of course, you need a computational pipeline because you're fusing data from lots of patches, right? You have these sensor patches in different locations. You don't know which one is giving the best signal, and multiple of them may be giving a good signal at any given time. So you're taking all of these signals, you're extracting features from these different patches, and then you're determining, you're classifying it, or you're reconstructing what the hard signal looks like. So you have to look at the signal quality across the different patches. You have to do sensor fusion, and also you have to deal with timing mismatches because the signal is not observed at the same time in all of these different patches. And of course, and finally, all of this depends on the individual. So all of this, different individuals can work extremely differently. The signals can look very different across different individuals. So no single model will work, well across everyone. So, we've shown that this can work really well across 20 subjects, men, women, and across different sizes, different body mass indexes, and so on. Now, this is just a very quick video, and so what this shows here is 4 patches signal on the top there, the voltage changing, and you can see as this person turns, their posture changes, so we detect the posture. And the signals also, you can clearly see the breathing waveform. You can also clearly see that the tossing and turning causes these 4 patches to observe different signals, which is what we leverage to do our detection. We've measured a number of other things. I'll briefly mention those as well. So for example, the Triboelectric sensor on the joints can measure these expansion and compression of these textiles, the crumpling that I talked about. And so from that, we've shown that you can measure all kinds of activities, just the daily activities that people do. In fact, we can also sort of see things like perspiration and, sweating. The textile sensors are also sensitive to those, so we can also get a glimpse at that information, which is valuable. We have also shown we've also designed a sleep mask, which can get at some of the most important signals in sleep, which is the EEG signal, the electrical signals from the brain. And we've designed the signal processing, the hardware, the signal processing, the data processing stages. And so what we've shown is, and this shows you a quick video of not the sleep part, but as my student is moving her eyes, you can clearly see the signal coming in from these textile-based sensors in the mask that she's wearing. So what we've shown is that the sleep parameters we obtain after all of the processing, the sleep parameters that we obtain from our Phi mask, which is what we call the device, is much closer to the ground truth polysomnography, which has a whole bunch of electrodes. This is a thing you would do in a sleep clinic, but it's a lot better than what you get from a Fitbit or an Oura Ring or one of these devices in the market. So all of our work has been published in very interdisciplinary forums, both on the computing side and on the material side. I wanted to thank the team which has worked on this, my chemistry collaborator, Trisha, ECE collaborator, Jeremy, and all of our students. Thank you.